Good morning, everybody. Welcome to lesson number 8 of the 21 we need to do to finish off this school year. Well, what we're going to do today is talk about yet another old crusty scientist from years and years ago named Pascal, right? And what Pascal's specialty was is he liked to study pressure, like we were talking about in the last lesson, but specifically he liked to talk about pressure when it's inside some kind of contained vessel. So the thing of today is going to be this guy right here. Right? If you've ever seen one of these before, this is called a Cartesian Diver. There it is, a Cartesian Diver for us. Now, Pascal, way back hundreds of years ago, certainly didn't have the 2-liter bottle. But if they existed, he would have loved these things, all right? Because it does a perfect example of what we need to talk about today. Right, so Pascal's interested in pressure, specifically inside of pressure, inside of a contained, some kind of sealed container and everything like that. So what we want to do is talk about, some of the things that he found out about it, right? And here's the big discovery. He finds out that pressure inside of a sealed container filled with a fluid, whether that fluid is water, kind of like this one, or just air, right? The pressure spreads out equally in all directions. So it pushes up at the top, pushes to the sides, right? Pushes down. It goes in all directions equally, right? This is where the first steam engine came from, right? Hopefully in social studies, you've learned about the Industrial Revolution. That's made possible because of something called the steam engine. And guess where that came from? All right, Pascal was one of the leading scientists to put forward the theories and do the research so that later engineers could come along and design the first steam engine. Now, normally in class, I'd have something very similar to one of these. It's not all fancy with lions and wings and things like that, but normally we would have that in class and I'd show you, right? And so all that happens is you've got a vessel that's got water in it. Right down below, you've got some kind of heating apparatus, right? So I would, in class, use the Bunsen burner. And basically, the water that's inside of it, right? The water gets hotter and hotter and hotter. And the hotter that the water molecules get, right, the faster they start moving, right? Normally, they're moving around, but as they get hotter, they get going faster and faster and faster and faster. Right now, eventually, the water molecules are going so fast that they can actually break through the water tension, that magnetic force that's literally trying to hold the water molecules, negative side to positive side together. They get going so fast they can break through that, and that's where you have steam, right? So that's where steam is going on there and everything. And in the case of this little drawing, right, the steam can come up and shoot out, from these little vents that they have for it. And what happens is this ball right here, it starts spinning faster and faster and faster. And that is the very first steam engine for it. So it's all thanks to pressure spreading out equally in all directions. So once you have a sealed container, right, that pressure is going all directions inside of it, right? So that is Pascal's principle. Normally we'd write this down, but you don't have to, right? The pressure is being transmitted or sent out equally in all directions, right? And so the example will be this guy right here, the pressure inside of a closed soda bottle. So you can do this at home. All you really need is an eyedropper, right, is probably the most technical thing that you might need to do this experiment at home. So let me cut to my kitchen really quick, and I'll show you the Cartesian Diver and then one other experiment going on about pressure really quick. All right, everybody. For our Cartesian Diver, if you want to try this at home, what you need is a 2-liter bottle, or even if you have one of those smaller plastic bottles to drink out of, you can. So you need that. You need to fill it up literally to the extreme tippy top with water right there. So I'm gonna fill this guy up. I've got a little eyedropper right here to get it as full as absolutely possible. Then the tricky thing for this is you need an eyedropper, right? And for the eyedropper to make this work really well, what you want to do is get the eyedropper probably about as full as possible when you're using it, and put it in a separate cup, and you want it to float, but just barely. So like if I push it down, it kind of goes down and eventually pops back up, right? And then what you're gonna do is you take this, you put it into your 2-liter container. If a little bit of water pours out the top, then you know you're doing this right. And then you need the lid, so you screw the lid on completely tight here. And what we'll do is we'll kind of clean up our mess and dry it off. And now I have my stunt Josiah with me, right, to test this out. Do you remember what you're doing for this guy? Right, so when you squeeze it, your Cartesian Diver goes down. Right, and so let me zoom in on this. Let me zoom in. There we go. All right, so here we go. Cartesian Diver goes down. Woohoo! So when you're squeezing it, it goes down. When you let it go, it goes up. Can you get it in the middle? Can you get it to stay in the middle? That's the challenge, is to get this to go in the middle. Normally, what we do in class, we'll do this experiment and we'll try to see who can hold it in the middle the longest without touching the top or the bottom. But that's the Cartesian Diver. You're changing the amount of gas that's inside of it and the water that's inside of it, and that's what's changing the buoyancy to happen for it. And then, are you ready to do our other experiment, Josiah?
Mm-hmm.
We'll see if it works with this. Hold on here. For experiment number 2, you're going to need a container, either a glass cup or this one's a plastic cup and everything. And then you need something to seal it that's going to be airtight. So in this case, we just have a big plastic lid that's flat. Or if you actually have a piece of cardboard, as long as it's a smooth, shiny kind of cardboard, that should work. Or even I've seen this done with just like you know, a note card, like a little note card and everything like that. So what we're going to do is we're going to put some water in our cup. I usually fill it about halfway up and everything. One trick to getting this to work is make sure the ring of the cup here has water on it, so it has a little bit of a seal. And then are you going to try for us? He's going to try. You just make sure when you do this experiment at home, make sure you do it over the sink. Yeah, do it over the sink, dude. Okay, so you put the lid on top, you flip it upside down, still no big deal, right? The water's staying in and everything. But then the big deal happens when you let the bottom go and it stays in there. Look, you've got all the mass of this water right here pushing down, but the plastic cup, in this case, is holding on, right? And the reason why is that air pressure, right? There's air pressure all around this. There's air pressure pushing this way, pushing this way, pushing this way, but some of the air pressure is pushing up, right? So much so that there's enough air pushing up on the bottom of this cup right here that it can actually support all of this weight right here, right? So that's another kind of cool thing that happens. And it'll stay like that indefinitely, right? The biggest thing, if you're trying to do this at home and it's not working, right, you're getting it to dump out, it means somehow air is getting into that seal right there. And that's why we wanted to make a little bit of water around the edges of it so that the air can't get in. As soon as a little bit of air gets in, whoa, the water can come out and splash all over. Did I get you? Yeah, now you don't have to take a shower today. Great. All right, so hopefully you enjoyed that right there and everything. So the Cartesian Diver with Pascal's principle, that's showing you that pressure that's going on there. So let me see if I can do this really closely for you and everything. I don't know on my computer here. Can I get this to work? What happens is when I squeeze on the bottle, I don't have to squeeze hard at all. But when I squeeze, what it's doing is it's increasing the pressure inside the bottle. And that pressure changes, right? As I squeeze on it, it changes the pressure inside of there. Now, inside that little eyedropper, there's a certain amount of air that's caught up inside of there. I'm trying to get it to hover here for you. There's a little bit of air that's caught up inside of it. If I squeeze the bottle, though, really tight, right, the air that's inside that little eyedropper, that little tiny bubble of air that's inside of there, when I squeeze the bottle, the air gets squeezed too, right? So I squeeze the bottle and the air inside of the eyedropper, it gets squeezed too and it gets smaller. So what happens is when the air amount gets smaller, it allows more water to come up in because of the pressure inside that eyedropper, and more water inside the eyedropper just simply means that now it's heavier and that's why it goes down, right? So that's, Pascal would have loved this thing. This would have been like one of his favorite toys. So you can see like trying to make it pop right here and everything for you. Right? Lots of air, little air, lots of air, little air, a little bit of air, right? You get squeezed, the thing goes down, lots of air, it goes up, right? Because that lots of air pushes the water out of the way, right? Same thing with the other example, right? With the cup and the piece of plastic. That one you definitely should be able to figure out some way to do at home as our kind of mini experiment for today. But same thing, pressure goes equally in all directions, right? So it's pushing up on that in that case and everything. Another example, and again, normally I would do this for you in class, is, hold on here. There we go. Let me, sorry. What we have is, we've got a pressure vessel right here, right? You've got this big glass container that normally I have in the classroom for us. And what they do is they have a vacuum pump hooked to it so that you can pull the air out. But, and yeah, you do there are all kinds of fun little things like balloons and everything like that. But normally, here's what I like to do, right? You take some peeps, right? Everybody likes tasty little peeps. Okay, I think they're gross. But most people like to eat peeps and everything. But when you put the peeps in, watch. You put that container over it, you pull the air out, and look what happens.
If you watch the peeps closely, you can see.
Oh, they're starting to burst almost.
They're starting to get bigger. They're starting to crack a little bit.
Right.
And kind of the neat thing here, they're getting really nice and big. That works really well. Kind of the neat thing here is that the elasticity of the peep is going to let it get bigger and bigger and bigger.
Oh, man.
And at some point, though, they're going to start to get a little bit smaller.
Oh, I'm seeing it happening. They're starting to shrink back down.
Yeah, we remove some of the air from inside. And of course, now, the fun part, of course, is always removing or letting the air back in. So there we go. And of course, the peeps even then get a little deflated, right?
Yeah, they look sad now.
As you would if you were put inside that chamber as well.
Poor peeps.
So,
they're not fluffy anymore.
They're not, because we've sort of ripped all those little air pockets, removed the air, and then the sugary goodness can sort of collapse back down.
They're kind of cold.
They're a little bit cold too.
Yeah.
Huh. So the peeps themselves, because they're sort of stretchy,
right?
They can only get so big.
Okay.
So,
but they got pretty big.
They did work really well. They got pretty big. So something that would not have that elasticity of the sugary stuff, shaving cream.
Okay.
So again, millions of tiny little air pockets inside this little thing of shaving cream.
Right, because when you first squirt it out of the can, I mean, it's all compressed in the can, and then
exactly, it's got all that,
right.
Got that sound. It's putting air pockets in there.
Okay.
Let's see what happens to the shaving cream.
All right.
Same
here
idea.
We go again.
We get tiny little air pockets inside there. We reduce the air pressure on the outside. Pressure on the inside is bigger.
Looks like a soft serve ice cream cone.
It does. It kind of looks like an ice cream, but it's going to get bigger and bigger and bigger. And because this doesn't have the stretchiness of the sugar with the peep, when we let the air back inside, this is my favorite part. It's kind of cool. And I don't know how much time we have to let it get big. You tell me.
We have a few more seconds.
All right.
We can let it grow a little bit here.
It's getting bigger.
It is much more dramatic. And again, it's just shaving cream, but there are so many tiny little air pockets. They're all expanding, sort of stretching the cream, making it bigger and bigger and bigger. And let's go ahead and let the air back inside dramatically, really quickly.
Let's do it.
What do you think is going to happen?
Go.
Oh!
And of course, and then,
someone's going to have to be doing the dishes tonight. All right, another example about pressure in contained vessels is something called the equilibrium tube. And for this equilibrium tube, again, normally we have this in class, right? The important thing for you to understand is all four of these tubes are all connected. So this really big one right here, there's an open tube connecting it to the other three. So this one is all connected too. When you pour the liquid in, oh, here, I clicked it already. When you pour liquid in, it doesn't matter which one of these you pour it into, right? The liquid spreads out evenly in all of them because the pressure is the same. So there's the same height in each one of these. Because of that, right? There's just as much water pressure, let's say, down here as there is down here or down here or down here. It doesn't matter at all the different shapes that you have, right? All the shapes that are different and everything, they all stay the same. Well, the amount of pressure stays the same inside of all of those for that, right? And then the last thing for today is the hydraulic press, right? Hydraulic systems are very, very important. We use them all the time. Well, maybe not all the time right now, but normally in normal situations where you're driving around in cars and trains and planes, they rely on hydraulic systems, all thanks to Pascal again, that made it possible. And they do two important things, right? First, a hydraulic system will multiply your work, right? And here's how it does it. There's kind of, imagine this is one setup right here. It's kind of simple, but it gets the point across, right? There's two hydraulic rams or presses right here. There's one small one over here, and there's a larger one over here, and they're connected, with some kind of little tube, so the pressure can transmit through it, right? So if you take this one and you push down, right? So let's say if this is 1 centimeter across, and you push down with 1 Newton of force, well, over on this side of it, it pushes up with, let's say, 3 newtons of force, because look, the 1 Newton of force that's pushing on 1 centimeter here, well, there's 1 centimeter here, there's maybe 1 more centimeter in the middle, and maybe another one on the side right here. So it pushes up with 3 newtons of force. So you push down with 1 Newton of force, it can lift up with 3 newtons of force. And this is just one example, right? You can have the difference between these be many, many hundreds of times in size. And so it's possible for you to push down with just a tiny bit of force. And if this one was really large, you could lift up like an entire elephant or something like that with relatively no problem at all. That's the beauty of a hydraulic system. So it multiplies your work and it also transmits it, or it sends it somewhere else, which also can be very, very handy. Let's say for a car right here, right? Well, for a car, if you're sitting in the passenger seat right here, well, first it transmits it, right? You can be sitting in, you know, relatively safety. You can be in your heated seats or air conditioning and everything like that. You tap the brake, and then that pressure goes all the way through the system to where the brake pads are, right? Imagine if to stop your car, you literally had to be right there by the wheel, grab the brakes and squeeze them yourself. That would be terrifying and dangerous, right? So it transmits it or sends it. Then the other thing, obviously, is it multiplies your work. You push just very gently, you know, when you're driving in a little bit here, right? You just tap the brake a little bit, but it sends a tremendous amount of pressure to the 4 brake pads, well, to the brakes. And so you just tap the brake ever so gently, and it stops thousands of pounds of people and cars and, you know, metal and all that stuff that's moving down the highway. You can stop it really, really quickly, right? And so that's, you know, that's the beauty of a hydraulic system. For us. So you can use it not just on cars, but on all kinds of devices, whether it's like construction equipment, forklifts. Oh, this car's got it. So like the doors and the hood and the trunk all open with hydraulic systems and everything, right? So that fluid, right, or that liquid, whether it's a gas or, you know, whether it's gas or a liquid, right? They're being transmitted equally in all directions, right? So that pressure is going to be the same at any point in the fluid, right, when it's being sent out equally. So in our case of our 2-liter bottle right here, the pressure, you know, when you squeeze, it's being pushed up, left, right, down, diagonal, right? That pressure is being pushed in all directions equally, right? This is where we use what's called a hydraulic device, right? It's just a machine that basically multiplies your work, right? So, you know, all you have to do is push a little tiny button like this guy's doing, and the cars are jumping up and down and everything, right? If you're a construction worker someday, or you know, rent a backhoe, all you do is move a little tiny lever, and it digs up hundreds, if not thousands of pounds of dirt and rocks and things like that. It's multiplying your work for you. Or how about this one? This is a simple hydraulic device right here, but yes, you could lift an entire car. You didn't know you had the superpower, but your superpower is called science. Because all you do is you just have to kind of crank the little handle right here, and it puts more and more and more pressure, and eventually you could lift up a car so high that you could walk underneath of it and change the tires or the oil or something like that, right? Those are all hydraulic devices and everything. Now, normally you have, you know, our example right here where you have worksheets to do and everything like that. You don't have to worry about the worksheets, but you do want to check, you know, in the lesson for today's folder and make sure if there's some videos for you to watch, and then there'll definitely be a quiz and there might be a reading. So just check the folder and that'll have all the stuff right there for you to do to get today's lesson done. Stay safe.